Okay, welcome back everybody for the fourth lecture by Remi Coulon on the twisted Patterson-Sullivan measure and applications to growth problems. So over to you, Remi.
Thank you very much. So let's finish the proof we started yesterday. So let me remind you first quickly what we have done and where we are. So remember, we had introduced a twisted Poincaré series, which is basically the standard Poincaré series, but where you add here in the sum the unitary representation on a Hilbert space H. And so that series, when it converges, is a bounded operator on a Hilbert space. And to such a Poincaré series, we associated a critical exponent, which is, so when you are above this critical exponent H rho, your series converges, and when you're below, your series diverges. And so the theorem we want to prove is the following. So if you take a Hilbert space, so you remember you need a partial order to have some monotone convergence. You take a unitary representation, then the two following statements are equivalent. So the critical exponent of your twisted series is the growth rate of the group G, that's one statement. And the other one is that your representation almost has invariant vector. And that was enough because, well, for our growth problem, that's enough because we observed that if rho is a representation from a group G into the unitary operators on the space L2 of G mod H, so when H is a subgroup, we prove that the growth rate of the small group H is always smaller than the critical exponent of this twist series and smaller than the growth rate of G. So which means now if the growth rate of H equals the growth rate of G, then the representation rho almost has invariant vector, which exactly means that the quotient is amenable. So that's why the statement about growth and amenability reduced to that statement about the critical exponent of this twist series. Okay, so now to get this, to prove this statement, we introduced twisted Patterson-Sullivan measures. So the idea is the following. Let me remind you how it goes. So we start exactly like the construction for regular Patterson-Sullivan measures. So you take the twisted Poincaré series, which I highlight in yellow, and then you add a Dirac mass at every point in the orbit, and you renormalize by somehow the total mass of this measure, which here will be the inverse of the norm of the twisted Poincaré series. And you do this for every point x in your space on which the group acts, and for every s which is strictly larger than H rho. And then we want to let this sequence of measures converge when s goes to H rho. But as we noticed last time, there is a trouble because the space of measure of operator valued measure is not a compact space in general. So we need to go through sort of side construction which involve ultra limits of Hilbert spaces. So we fix a non-principal ultra filter so that we can define a limit Hilbert space, which is the limit of a sequence of Hilbert space Hn, but here we're using Hn to be always the Hilbert space we started with. And then now we are going to define a measure that will take value in the bounded operator of H omega. And you do it as follow. So basically, we sort of mimic the weak star topology. So the way we define this new metric is this new measure is by defining what is the integral of this measure of any continuous function. So the integral of f against ax, that's the limit in the sense of the ultra limit of the integral of f against dx Sn, where Sn is a sequence that tends to h root. So again, just to make sure that we know what the objects are, so this is here a bounded operator in H. I'm wrong. This is here. This integral here is a bounded operator on H. And so when you take the limit, what you get here is a bounded operator on H omega. And so all this measure here indexed by the point of the space, Ax, we call that the twisted Patterson-Sullivan density. And now, what are the main properties, and then the most straightforward properties we can get from those Poincare Patterson-Sullivan measures? Well, so first, I claim that the measure is supported on the boundary. So here, as I told you, I'm cheating a bit. So the reason is the following. Let me go back to the previous slide. So if you look at the measure AXS, so if you want the limit measure to be supported on the boundary, basically you want your renormalization somehow to kill everything that takes place inside the space X. And for this to happen, usually the way it goes is that that would be the case if the norm of AS diverges to infinity when S approaches H rho. So typically, if that series diverge at the critical exponent, then the norm will kill everything that takes place inside the space. And I treated it the same way for the standard Patterson-Sullivan measure. So the construction I worked would work if the series diverge at the critical exponent. But it may not diverge at the critical exponent, but then there is a little adjustment in the weight you can put in the Poincare series to make sure that with the same critical exponent, it diverge at that critical exponent, and you're good to go and everything will follow. So since it will not affect in any essential way all the rest of the arguments, I prefer to cheat a bit here. So the construction is not exactly the one you run, but that's the idea. So that's why you get a measure that is supported on the boundary. Then, well, you have a normalization. So if you compute what is the total mass of this measure, AO, so the total mass, that's the integral of the constant function, and this mass is an operator again. This measure takes value in the space of operator. So the way we normalize that is like saying that this total mass is an operator of norm 1. So in particular, it's not 0. That's the main thing I have in mind. That's not something which is 0. And then, so if you remember, we had some invariants by the group for regular Patterson-Sullivan measure. So here we get this similar invariants, but because we twisted the Poincare series and all construction by representation, we get a twist, which I highlighted in orange here. So when you push the measure AX by any element G, you get the measure A at GX, but precomposed by the limit representation rho omega. And that twist will be very crucial later. The proof, just abstract nonsense. You write down what is this measure when you have, before you go to the limit. So G, when you push AXS by G and AGXS by G, you write down what's going on, you pass to the limit and you get the identity. So exactly like the regular Patterson-Sullivan measure, just pure abstract nonsense. And then we also have a conformality So again, I highlighted in orange what is different from the standard Patterson-Sullivan measure. So here I claim that the Radial Limit Derivative of AX with respect to AY is still this exponential minus h rho, the Boozman function axis of x and y. But if you think a bit, so the Radial Limit Derivative should be an operator, because what you want to write is something like this. You want to write that the integral of f dAx equals the integral of f, something here, which is the Radial Limit Derivative, times day. So since morally this day is an operator, you want to apply another operator on it. So that's why I wrote it in this way, saying that this is this exponential minus h rho Boozman of x and y times the identity. So just a warning here. In general, if you have operator valued measure, this notion of Radial Limit Derivative is not well defined all the time. It may not exist. So here we can prove that what I wrote makes sense, but this is not just some general result about measure theory. There are really some subtleties that may arise when you consider operator valued measure. But anyway, the proof, basically, it's exactly the same proof that the one we did for the standard Patterson-Sullivan measure. I'm not going to redo it. You just copy your proof. You just carry the twist everywhere in the computation, and you get the exact same formula. So there's nothing serious in terms of technology here. Okay. Any questions? Okay, if not, let's move to the main consequences of those properties. So let me recall you the shadow lemma that we proved for standard Patterson-Sullivan measures. So basically, when you have a conformal G-invariant density on your boundary, then you can measure the mass of certain shadows. Oops, that's not the tool I want here. And the mass of the shadow is essentially exponential minus hgt stand from O to G. So just for a reminder, the shadow here is you have your space X, you fix a point O in the space, GO maybe somewhere here, you choose a little ball of radius R around GO, and now you consider all the points which are behind this ball seen from G. So that looks something like that, from O, sorry. So if I start from O and I look at all the points which are behind the ball, I get a certain set, and this set is the shadow seen from O of GOR. And the importance of the shadow lemma is it gives you an estimate for what is this measure. The measure of the shadow is essentially this term. So if you remember the original shadow lemma, we also had somewhere in the formula the total mass of nu of GO. But since here I'm considering a measure which is G invariant for the whole group G, not for just a subgroup, this mass is just always 1. So it will not arise in the statement. Okay, so and how we prove that shadow lemma? Basically, we only used the equivariance and the conformality of the Patterson-Sullivan measure. So in the exact same way, you can also just copy-paste the proof. In the exact same way, you can prove the following half shadow lemma, saying that now if you measure the mass of a shadow, but now for the operator valued measure, and compute the norm of that operator, you get an upper bound which has the same kind of flavor. So exponential minus h rho distant from O to GO. So the only difference is the critical exponent. Here we had hg for the standard Patterson-Sullivan measure, and for the twisted Patterson-Sullivan measure, the exponent we have here is h rho. But that's the same kind of flavor. So now, once we have that, I can give you very quickly what the outline of the proof will be. I'm going to cheat a lot, but we will go through the details after and fix all the problem one after the other. So
Remi?
the first, yes.
Is it maybe I misremember, but in the previous shadow lemma that you have, didn't you have only some H invariant densities?
Yes. So the shadow lemma work for any H invariant density where H is a subgroup, a normal subgroup of G. But here I'm using for H the whole group. So I take now a G invariant density and I apply the shadow lemma for this G invariant density.
Okay.
Does that make sense?
Yeah, sure.
So yeah, so sorry, maybe one thing which may be confusing is that when we prove the easy direction using Roblin's method, we were using H invariant densities. Here, there will be no more H invariant densities because, as I told you, somehow the twisted density will package all possible H invariant density. So the H invariant density, somehow they are hidden in the twisted measure. And for the standard measure, standard Patterson-Sullivan measure, I will only consider G invariant H conformal densities. And so that's why I have this somehow weaker shadow lemma, but that's why also I don't have the total mass which appears in the formulas.
Okay, thank you.
You're welcome. So now what's the heuristic of the proof? So recall the assumption is H rho equals Hg. So those two critical exponents are the same. So roughly speaking, now compute the mass of this shadow here for the twisted measure. That's an operator. I compute its norm. And up to a constant, the half shadow lemma tells me that this is at most exponential minus h rho distant from O to GO. But because h rho is the same as hg, this is also exponential minus hg distant from O to GO. But now I use the regular shadow lemma, and it tells me that, well, up to a constant, this is the mass of the same shadow, but now for the regular Patterson-Sullivan measure. So roughly speaking, I'd like to say that this twisted measure is absolutely continuous with respect to the standard Patterson-Sullivan measure. And when I go from here, from this statement on shadows to this claim that AO is absolutely continuous with respect to nu O, I am cheating a lot. So I'll explain later how you can fix that. But that's the idea. So you from this domination you get on shadows, we deduce that AO is absolutely continuous with respect to nu. Okay, so then when you have two measures like this, the standard things to do is to consider the Radial Limit derivative. This notation, Radial Limit derivative, again, I'm cheating a lot because there is no Radial Limit theorem for operator valued measure. But forget about that. So the Radial Limit derivative of an operator valued measure with respect to a real measure, what should it be? Morally, that a function from the boundary that takes its value in a space of bounded operators. And now, if you just write down what the conformality and the equivalence of those both measures gives you, you will obtain that this operator D, this function D, satisfy a certain equivariance property. So D computed at GC, that's DXC where you applied the twist, here the representation G omega, rho omega at G. So that's one feature. But on the other side, we will see that the action of G on the diagonal action of G on the boundary times boundary is ergodic, and that will force this map D to be essentially constant. So now if D is essentially constant, this D of GC and this D of C, they are the same. So if you write down what it means that the image of D is a space of invariant vectors for rho omega. But since our original measure AO was not the zero measure, this was, as we saw with the normalization, D is not the zero map, so the image is non-trivial. And so in the image of G, you get non-trivial rho omega invariant vectors, which is exactly what we were looking for. So that's the general strategy. But as I told you, I cheated quite a lot on the way. So let's now go back to the proof step by step and fix all the parts which are a bit fuzzy. Well, before I do that, do you have any questions? Well, if not, then let's go on. So what was the problem with this shadow business? So let me do a very vague picture, but so here is my space X, and I have some points in the orbit of G. So this is elements in the orbit of G. For instance, this is GO, and let's say I have O here. So let's, I don't know, consider a certain ball here, and then we have behind this ball, we have its shadow. So seen from, oops, that's what I want to do. So seen from O, that's the shadow here. So, but imagine, as in this very rough sketch, that the set that I can, well, the shadow allow you to approximate some sets in the boundary, some stuff which is here, some stuff which is here. But you may have trouble if some of the mass of your measure is, for instance, here, or even quite close here. So if you have part of the measure with a positive mass that you cannot approximate by arbitrarily small shadows. If you have such a thing, maybe you know something about the shadows, how you compare the measure on the level of shadows, but that will never give you something at the level of the measure on the entire space. So for the argument of the absolute continuity argument to work, we need to make sure that we can approximate, well, we need to make sure that the measure gives mass to subset that can be approximated by arbitrarily small shadows. If not, then the argument will not work. So that leads me to consideration on what's called the radial limit set. So let me define what the radial limit set is. So I consider my space X always here, and I fix a point C and consider a geodesic from, let's say, the base point O to C. And I will say that the point C here belongs to the set lambda rad K if the ray from O to C intersect infinitely many translates of K. So if you have infinitely many translate of K here. So these are points at infinity where, if you think in the compact, in the quotient space, it means that your ray is returning infinitely many often to a given compact part of your quotient. So that's the definition of this set lambda K rad. And the radial limit set is the union of all those lambda K rad. So say differently, to relate that to the shadows, that's something you can work out as an exercise. So a point C will be inside the radial limit set if and only if there exists a certain number R and there exists a sequence Gn of elements in a group such that the point C will belong to all the shadows from O of Gn O with radius R, so for every n in n. So this is typically the kind of set that we can approximate by arbitrarily small shadows. So now the one crucial argument is that if the action we started with is strongly positively recurrent, then we can find a certain compact subset K such that this partial radial limit set lambda rad K has full measure both for the standard Patterson-Sullivan measure and for the twisted Patterson-Sullivan measure. And this is the only crucial place where we will use strong positive recurrence. Everywhere else, you'll see you can work out the argument by assuming that group G, say, is divergent. But here, really, we don't know. Well, we cannot do without assuming that the action is strongly positively recurrent. So the proof of that part is quite, you do that really by hand. It's a bit technical, so I'll skip it for the moment. And if we have time at the end, I'll come back to it. But this is really the only place where we use a strong positive recurrence. So, and now, because this radial limit set has full measure both for the standard Patterson-Sullivan measure and the twisted one, we can use the shadow to compare the two measures. And you can play a Vitali type argument. And the outcome of that argument will be a statement of this kind. So every time, every time you pick a continuous function on the space X bar, so on one hand, you can compute what is the integral of f against the operator valid measure. So again, that's a bounded operator. So I can compute the norm of this bounded operator. And this will be at most a constant time the integral of the absolute value of f against the standard Patterson-Sullivan measure. So this is exactly what we get from the comparisons on the shadows and the fact that the radial limit set has full measure for the standard Patterson-Sullivan measure and the twisted one. So just another way to reformulate this statement is that if you have a map, so we have a map from the space of continuous function on X bar to the bounded operator on H omega, which sends every function f to the integral of f dAO. And now what I claim, what this inequality is saying, that this map is continuous, but not for the infinity norm on the space of continuous function. It's continuous for the L1 norm on the space of continuous function. So we can extend it to actually a function from L1 of X bar nu O to space of bounded operator. So what we get is a linear function which is continuous now for the L1 norm. Questions?
Remi?
Yes?
So you said that you only use this strongly positively recurrent for this proposition in the proof?
Yes.
So is there any chance that being a strongly positive recurrent is equivalent to this other condition that there is this compact set? So can this proposition be an if and only if, or?
I don't think so. I don't have an example here, but I'm not sure. I don't think so.
So in theory, your theorem can be like a weakening, putting this other hypothesis that there is this compact set.
Yeah. So if you know that for this twisted measure there is a compact set such that lambda rad k has full measure, all the rest will follow.
Okay.
But yeah, I'm not sure about this, so I need to check. Okay, so now basically this inequality that I wrote here, that's a more rigorous way to say that AO is absolutely continuous with respect to nu O. So now we want to consider Radial-Limit derivative. So as I told you, in general, there is no Radial-Limit theorem for operator valued measure. So the way we do that is the following. So I fix a vector phi in my Hilbert space H omega. And then for this fixed vector, I can compute those kind of integrals. So I compute the integral of f dAO, so that's an operator. So it eats a vector. And in this way, so I can think of this as being a function from Cx of the continuous function on X bar to H omega, which to every function f sends you the integral of f dAO applied to phi. And now so I have a function. Well, actually, it's I started from the continuous space of continuous function, but that's, as I told you, it works from the, if I start from the L1 function, I have a continuous function of this form. And now you can think of this as a Hilbert valued measure on the space X bar, or on the boundary, because it's supported on the boundary. And now for Hilbert valued measure, because Hilbert space are uniformly convex, on a Hilbert valued measure, you have a Radial-Limit theorem. So you can consider the Radial-Limit derivative of this new Hilbert valued measure with respect to d nu O. And this Radial-Limit derivative is what I wrote d of phi here. So I would prefer to have an operator, but here there is a subtlety. So the rigorous way to say it is that we have a map T that takes any vector h in h omega. So that vector is a vector phi below, that returns a map, a bounded map from the boundary of the space to the Hilbert space h omega. So d phi here is a function from the boundary of x to h omega. And this identity is just saying, is somehow saying that d is the Radial Limit derivative of the Hilbert of the operator valued measure with respect to the standard Patterson-Sullivan measure. So this is the proper way to write down the Radial Limit derivative. I'm not entirely sure if there is a way to go directly and say that to define dAO over d nu O directly, but okay, this is a trick we can use. So we are going in the rest of the proof to argue always pointwise. So we always fix a vector phi in h omega and apply all the operators we constructed on that vector phi. Does that make sense? Okay, so yeah, is there a question?
That's fine.
Okay, so then let's try to understand what we can deduce from this Radial Limit derivative. So somehow, the very vague analogy you can keep in mind is on the first day, we try to understand the case of the free groups using operators. And we had the regular standard operators, which was just the adjacency matrix of my automaton, a twisted one, and in the story we had other ingredients that play an important role, where the spectral radius of those operators, and eventually some almost eigenvectors. So somehow what's going to happen here is that the standard Patterson-Sullivan measure play more or less the role of the standard operator. The twisted Patterson-Sullivan measure plays the role of the twisted operator. The critical exponents which are associated to those measures are like spectral radius of my operators, and the Radial Limit derivative will play the role of almost eigenvectors. So this is really the analogy. I'm not sufficiently expert to push this analogy, explain you why that's the right way to think, but this is the analogy we kept in mind during all the work we had done. So with these analogies in mind, my goal is to prove that the Radial Limit derivative somehow is an invariant vector. You remember the first lecture, we proved that the eigenvector of the twisted operator were actually invariant vector for the representation, or almost eigenvector were almost invariant vector for the representation. So we are going to try to prove the same kind of things. So the first statement will be the following one. So I fix a vector phi in my space, h omega. So as I told you, everything will be done pointwise. And now I consider the map C. So if you remember, C, that will be a map from the boundary of your space to h omega, and a bounded one, that's a bounded map. And I claim that this map satisfies the following twisted invariants. So let me do the computation. So what we will do is we will compute in two different ways the following integrals So the integral of f d of G inverse star AO. So first computation, I will push everything on the side of standard Patterson-Sullivan measure and then use the properties of the standard Patterson-Sullivan measure. So to do that, well, just do a change of variable. That will be f composed with G inverse DAO. But because of the identity we had before, so this one, I can rewrite this integral. Sorry, I will always forget that. I compute this against, so let me write this properly. I always compute this on a given vector. So this is apply to phi equals this, apply to phi. And so now I use this identity here. So if I use this identity, this part here will be my vector psi. So that vector is exactly the integral of f composed with G inverse psi d nu O. So same change of variable, but in the other direction, you have f times psi composed with G d of G inverse nu O. But now the measure here, the density I have is G invariant. So I can push the O inside the measure, so that the integral of f psi composed with G d of G inverse O. And now what I'm going to do is to use the conformality of the regular Patterson-Sullivan measure. So I can rewrite this as the integral of f times psi composed with G. And I want to have, maybe I should not write it like, I should leave a blank here, psi composed with G. And now I want to write here the Patterson-Sullivan measure at O. So to do that, I have a term here which would be Hg distant from, not the distance, Huysman function at xi between G inverse O. Does that make sense? So I push everything, using the Radial Limit derivative, I push everything on the side of Patterson-Sullivan measure, the regular one, and then use conformality and invariance. Now let's do the same computation, but now I will directly do this conformality and invariance on the side of the regular Patterson-Sullivan measure, of the twisted Patterson-Sullivan measure, sorry. So I compute d of G inverse AO and everything apply to psi. So this is now the twisted measure is also invariant. So I can write this as d of A G inverse O. But if you remember, the invariance had a twist. So what I get is here, there is a representation rho omega computed at G, which appear when I do when use the invariance, and everything apply to C. So the integral somehow is linear, so I can take the representation outside of the integral, and you get the integral of f d of A G inverse O apply to phi. And now I use the conformality of this measure A G inverse O to go back to the measure AO. So I get the representation rho omega, the integral of f exponential minus h rho Guzman at C between G inverse O and O times D O apply to phi. And now again, now I will push that thing on the level of regular Patterson-Sullivan measure using this Radial-Limit derivative. So this is exactly rho omega G times, I don't need this bracket anymore, the integral of f exponential minus h, minus h rho Guzman at C G inverse O psi times d nu O. And if you compare with what we had done before we had the following thing. We had the integral of f exponential minus h g Guzman at C between G inverse O psi composed with G d nu O. And this is true for every continuous function on the space. So it means that this term here applied to psi needs to equal this term here. So if I rewrite, this is exactly what I was looking for. What we get from here is that rho omega G applied to psi equals psi composed with G. So this is just, writing the invariance, eventually twisted invariance, and the conformality on both sides. And since one has a twist and the other has not, you get this twisted invariance relation on psi. Does that make sense? Okay, then we need some ergodicity, I told you. So here we're going to use the Patterson-Sullivan theorem. So that's a very general statement which says the following. So if you have a group G acting properly by isometries on the cat-1 space, I said I will stick with cat-1 spaces. It's also true, you had to adapt it a bit, but it's also true for hyperbolic spaces, but it's much more painful to state correctly. So let's stick with cat-1 spaces. So when you have the group acting on a cat-1 spaces, there is a lot of properties which are, a list of properties which are equivalent. So the first one is the action of the group is divergent. So remember, it means that the Poincare series diverges at the critical exponent. Second property is that the Patterson-Sullivan measure charges only the radial limit set. Third, if you look at the geodesic flow on the quotient space, that geodesic flow is ergodic for the Bowen-Margulis measure. And the last property is that the diagonal action, there is a gamma, it should be a G here. The diagonal action of G on boundary times boundary is ergodic. So if you remember the statement I gave you before, we have seen that when the action is strongly positively recurrent, then the Patterson-Sullivan measure only charges the radial limit set. So here 2 holds, which means that now we can use the fact that the diagonal action is ergodic, which is the part I'm interested in. So I will not explain the details of these proofs. These are very standard arguments. Just maybe for your knowledge, say what is this Sx is unit tangent bundle somehow here in the context of the cat-1 space. So if you think of a cat-1 space, X, so you have your space inside and the boundary at infinity. So if your space is a hyperbolic space for which you have a differential structure, when you take a vector, a unit vector, that will define you 2 points in the boundary, which is somehow the point you get if you follow the flow at infinity, and I call it V plus, and the point you get if you follow the flow backward at minus infinity, and it gives you V minus. So for each tangent vector, you get the 2 point at infinity, and somehow the only thing which is missing to completely characterize this vector is where it is located along this blue geodesic. So for instance, you can fix a certain reference point O and say, well, one possible way is project the point O on this geodesic, and you will say, let's say time 0 is when the vector is attached to the projection of O. And this will give you naturally an identification between the unit tangent bundle on the space X with something which is d2x times r, where d2 partial d2x, this is just the boundary times the boundary minus the diagonal. So these are called the Hopf coordinates. For your unit tangent bundle. Well, so this was to give you a parameterization of the unit tangent bundle when your space is really a simply connected hyperbolic manifold. If you don't have that manifold structure, you cannot speak about the unit tangent bundle. But you can always consider the Hopf coordinates. Boundary times r. It's a well-defined space. And that will be what you call in general this SX. This will be just this space here. And you have a flow, which is just translation on the r coordinate. And that defines the geodesic flow. And the orbit of that flow, when you project in the space, there will be geodesics. And on this space X, SX, you can put a measure, which is basically is d nu O times d nu O times dt, and well, you need to renormalize by something here. I don't want to spend too much detail here, but you renormalize by something, and you get a measure that will be G invariant on this space SX. And that's a measure which is called a Bowen-Margulis measure. And that gives you then a measure on the quotient space, and that is the meaning of this sentence here, that the geodesic flow on Sx mod G is ergodic for that particular measure. So, and the proof is something called the Hopf argument. If you know this, that's good. If you don't, you can Google it. That's a very standard argument. Okay, so how are we going to use this ergodicity now? So remember, my goal is to prove that this map C, we already proved is equivariant. I want to prove it is constant. So the first remark to do is the following. So imagine the following situation. So you have a function f that goes from the boundary to R, that is G invariant, almost surely, nu or almost surely. So meaning that f of gc is f of xc. So because the group G is divergent, the action of G on the boundary endowed with the Patterson-Sullivan measure is ergodic. And when you have an ergodic measure, a G invariant function has to be essentially constant. So this is exactly the kind of argument we want to play. The trouble is that our function goes from the boundary to our Hilbert space. And the invariance we have is not the standard invariance, that's a twisted invariance, meaning that psi of g c is rho omega g of psi at xi. And because of that, we cannot directly use the ergodicity of the group on the boundary. We will need the ergodicity of the group of the double boundary. So here is how the argument works. So if I want to exploit the ergodicity, I'm going to consider a map Q from the boundary times the boundary to R. And it will send the vector, the pair xi eta, to the scalar product psi of xi, psi of eta. So now if I use a twisted invariance for psi, you can observe that if I compute Q of g xi g eta, here the g that is inside the psi I can take it out if I replace it by the representation rho omega. So twisted invariance give me something like that. Rho omega g applied to psi of xi, rho omega of g applied to psi of eta. But remember, rho omega is a unitary representation. So I can somehow cancel those two representations, and I'm left with Q of xi eta. So which means that Q is now G invariant for the action, diagonal action of G. So by ergodicity, it means that Q is essentially constant. And let's say it's equal to a constant C. So now how do we go from here to saying that psi is constant? So basically, it's an argument which is Cauchy-Schwarz inequality. So maybe I should take another page. Let me add one page. Sorry, here it is. Okay, so consider two functions, f1, f2, which are continuous. And I'm going to consider the scalar product integral of f1 psi times d nu o, integral of f2 psi times d nu o. Okay, so we are integrating function with value in a Hilbert space. You should not be afraid with that. Formally, everything works in the same way. So especially, I can take out the integral outside of the scalar product and move it back inside when needed. Everything is linear. So I have here a double integral of f1 xi f2 eta times scalar product psi of xi psi of eta d nu o of xi d nu o of eta. But this is exactly, since this function is constant, this is c times the integral of f1 d nu o times the integral of f2 d nu o. So I said the scalar product is constant, and then I split again my two integrals using Fubini. So in particular, imagine now that f is a positive function. If I apply this with f1 equals f2, what I get is that on one side, I get the integral of f psi d nu o, and what I get is exactly the square of the norm. So I take the scalar product of the vector with itself. And this scalar product is now c times the integral of f d nu o squared. So it implies that the norm of this integral, forgot the psi, is exactly square root of c, the integral of f d nu. So now if I rewrite the line above, I will rewrite it with f. So I will rewrite it now with the function f, and here I will take the constant function equals to 1. So if you write this, you have the scalar product of f psi d nu o, scalar with the integral of 1. So, well, I can remove it. There is nothing here. Psi d nu o. And this term will be exactly the norm of the integral of f psi d nu o. And this term will give me the norm of the integral of psi d nu o. So you see, we are exactly in the equality case of the Cauchy-Schwarz inequality. So that implies that the integral of f psi d nu o is equals to a certain number, let's call it lambda, that depends only on f, times the integral of f d nu. And this is true, again, for every continuous function. Well, here, positive continuous function, but this is true for every continuous function. And so this is now a very basic thing of integration, to see that it will force C to be essentially constant. The only way you can get that is phi is essentially constant. So we used the double ergodicity to get rid of the twist that appeared in the equivariance of psi. And then this is just a Cauchy-Schwarz inequality, exploiting the equality case of Cauchy-Schwarz to prove that psi is essentially constant. Does that make sense? Okay, so now let's summarize where we are. So we started by assuming that the critical exponent of the representation is the same as the one of the ambit group. So the first step was to build a twisted Patterson-Sullivan measure following the same construction as a standard Patterson-Sullivan measure. And we proved then similar properties like equivariance, conformality, etc., etc. And especially we also get a shadow lemma. And now using this shadow lemma and the strong positive recurrence, we were able to prove that A naught is absolutely continuous with respect to nu naught. So when you have absolute continuity, you consider the Radial Limit Derivative, which, to be rigorous here, was a map from h omega to the L infinity space of function from the boundary to h omega. And so what we know is that this map D is non-zero because the total mass of the measure AO is an operator which has norm 1. So in particular, I can consider a vector phi in h omega here, so that psi, which again, psi is a priori a function from the boundary to h omega, that function is non-zero. We prove that it is essentially constant and it's also equivariant. So meaning the essential value will satisfy rho omega g psi equals psi for every g in the group. So which means that this essential value is a non-zero invariant vector. And that's exactly what we wanted, because a non-zero invariant vector for the limit representation rho omega gives you almost invariant vectors for the initial representation. And so that's the end of the proof. Questions? So I don't know if I killed you on the way. Since we have time, I can explain you where the strong positive recurrence assumption plays a role and how we prove this proposition that I left on the side for the moment. So
Yes, please.
okay, so let's do that. So essentially, I will do some pictures because computation can be sometimes a bit crazy, but I'll try to give you the idea. So here's a proposition I want to state. So if you start with a group acting on a space X with an action which is strongly positively recurrent, I want to prove that for some compact K, the Patterson-Sullivan measure, I will focus on the Patterson-Sullivan measure. Patterson-Sullivan measure has a full measure. The radial limit set has full measure for the Patterson-Sullivan measure. The space for the twisted one, exactly the same. So to do this thing, somehow we are going to go back to the definition of the Patterson-Sullivan measure and use the measure nu OS before we took the limit. We will try to understand those measures and then pass to the limit. So the way to do that is to introduce a space LK, which are the point C, which are the endpoint of some geodesic. So that's a geodesic ray which such that if you intersect gamma with the orbit of K, this is contained in K. So it should look a bit familiar with what we had done for the definition of strongly positively recurrent actions. So if I do a picture, the situation is the following. So I have the compact K, and I look at a certain ray from K to the point C. But what I want is that along the way here, oh, that's big. So what I want is that along the way here, I am never intersecting any other translate of K. Okay? So why am I interested in that space? It's because of this remark. If I look at the whole boundary and I remove from the whole boundary the K radial limit set, basically that's contained in the orbit of this space LK. Why is that? Well, probably the best is to redo a picture. So let me rewrite this identity. So the boundary minus the radial limit set, the K radial limit set, is contained is the orbit of LK. The reason is the following. So let's start with the space X. And now I have a point here, which is in the boundary, but not in this K radial limit set. So if it's not in this K radial limit set, what does it mean? It means that I may intersect several copies of my compact K, but after a certain time, I never intersect any other copy of that thing. Here, I don't want the same color. Here, somehow, on that part, I never intersect any other copy of K, because it's negating the definition of being in the K radial limit set. These ray will intersect only finitely many times translate of K. So in particular, what does it mean? It means that this point here, if I translate it by G inverse, well, I will get a geodesic that starts from K going to Xi that never intersect any translate of the compact K. So G inverse Xi here belongs to LK. So in particular, Xi belongs to G of LK. Okay? So what I want to prove is somehow that this set G of Lk has measure 0 for the Patterson-Sullivan measure. But the point is that G is a countable group. Because the action is proper, it's an increasing union of finite sets. So G is a countable group. So I have a countable union of subset. If I want to prove that it has measure 0, it suffices to prove that Lk has measure 0. So that would be our goal. The goal would be to prove that Lk has measure 0. So what we're going to do is consider a certain neighborhoods of that space Lk, which are defined as follow. So I would consider a subset UKT, which I'll write the definition and I then draw the picture to explain what's going on. So there's a set of points in the space union its boundary, so in the compactification, such that there exists a point in this space Lk for which the Gromov product Cx seen from O is bigger than, let me say right, strictly bigger than a parameter T. So the picture is the following. I have my space X. Here is the base point O. So I can take a point either eta or on boundary or a point X inside the space. Imagine I have a geodesic that goes from O to one of these points. Then I can find another geodesic that will go from O to a point C, but that point C being in Lk, so that the length on which they fellow travel, two geodesics that start from the same point, they will fellow travel for a certain time before they diverges, and the length for which they fellow travel, roughly speaking, is T. And so the important fact somehow is that UKT will be a neighborhood of Lk. So now I want to understand what is the measure of this neighborhood. Because if I can have an upper bound on the measure of this neighborhood, I will get a control on the measure of Lk. And to get an upper bound of this measure, I will go back to the initial construction of the Patterson-Sullivan measure. So the initial construction was a measure which is distributed on the orbit of the group G. So what I'm interested in is to understand what is this subset, so UKT, which is my neighborhood of Lk, intersected with the orbit of G. And I claim, so here I'm a bit fuzzy, so it's not totally rigorous, but that's the idea. I claim that this is contained in the union for all U in the subset GK. So remember that subset GK, that's the one which was responsible for the lack of convexity of the orbit, of the shadows seen from O of UO and some R. So how do we prove this thing? So how do we prove this claim here? So do you have another page? Yeah. So let me do a picture. That's always a good thing to do. So I start here. I take a point now, GO, which belongs to UKT intersected with GO. So here is O, here is some GO, and let's have a geodesic from O to GO, like that. So by definition of UKT, it means that there is another geodesic starting from O that goes to a point C, which is in LK. And those two things here fellow travel for a time t. So imagine now I have a certain, the geodesic C start from a certain compact K here. That's my compact K. Oops, that's too big. And what I know is that along the blue geodesic, the dark blue geodesic, I never intersect any other translate of K. So on the light blue geodesic, well, maybe I intersect a translate of K because I need to intersect these translate here of K. Here I have GK. So maybe I can intersect another translate of K, but not on that part which fellow travel with the dark blue geodesic. So what I will do, I will consider another translate. The first translate of K, I may intersect when I start from O and follow the light blue geodesic. So the first translate of K I intersect, let me call it UK. And so somewhere around here, you have UO. So the observation is that U, well, that's an element in GK by construction, because from O to UO, the geodesic does not intersect any translate of K, but K and UK. So by definition, that's an element in GK. First point. Second point is that the distance from O to UO, well, roughly speaking, is larger than T, because I know that during this time T, where the two blue geodesic fellow travel, I cannot intersect any compact K. So there is some neighborhoods here you may have to add because they fellow travel with a certain constant delta, but that's the idea. So there would be no compact here in between. So this distance is at least T. And then just by some construction, GO, the geodesic from O to GO pass by UO. So it means that GO is in the shadow from O, seen from O of U or R, and R will be basically the diameter of your compact. So that's it. So we have proved that UKT intersected with GO. Sorry, it's not an index. That GO that contain into the union for all U in G index K of the shadow seen from O of UOR. And here that's the important fact that distance from O to UO is larger than T. Does that make sense?
Yep.
Okay, so here again, I'm fuzzy because if you want to be completely careful, this will not be GK, but a finite set of translate of GK. And there may be some thickening of compact you need to do because of hyperbolicity. A lot of details that need to be worked out properly, but the idea is this one. So from there, let me add one more slide. Oops. Can I go directly to the last one? Yeah. So from there, I can compute now what is the measure of this set. I want to compute what the measure nu O of this set UKT, but I will compute it for the measure we constructed before we passed to the limit. So that measure was exactly, supported on the orbit of G. So that's the measure of UKT intersected with GO. And so therefore, it's at most the sum for all the elements U in GK with the distance from O to UO bigger than T of the measure UOS of the shadow UO from O of UOR. And now I'm going to do something horrible. I'm going to pass the limit. So why is it horrible? Because the convergence we use when we construct the Patterson-Sullivan measure is a weak star convergence. So I cannot say that the measure of a Borel subset for nu O is just the limit of the measure of those subsets for nu OS. In general, you cannot say that. But somehow the sets we are considering are open sets. So as I told you, this thing is an open neighborhood of my space LK, and those shadows basically you can think of as open sets. So I claim that you can justify this carefully and you can pass to the limit. Here, I'm a bit cheating. There is some careful analysis to do, but basically you get at the limit that the measure of UKT for the Patterson-Sullivan measure is at most the sum over all U in GK, such that the distance from O to UO is bigger than T of the measure of the shadow here from O to UOR. But then I will use the shadow lemma to get an estimate of those shadows. And what we've seen is that up to a constant, essentially what I have is the sum over all elements U in GK, that the distance from O to UO is at most T, exponential minus HG, distance from O to GO. So what you see here, this series, this is the remainder of the series exponential minus S distance from O to GO, where G is an element in GK and S equals HG, right? But because, so if now, yeah, I'll probably add one more slide. That would be go back. So what we had is that the measure of UKT is at most up to a constant, the sum over all U in GK, such that the distance from O to UO is bigger than T of exponential minus SG, distance from O to GO. And what we know is that if K is large enough, so the growth rate of that subset GK will be strictly smaller than the growth rate of G. That's because the entropy at infinity of G is strictly smaller than Hg, and this entropy at infinity is exactly the infimum of all the Hk or all the entropies of the GKs. So which means that this series here, if I sum over all elements U in GK, this converges at Hg. And since here I have a remainder, so I only consider elements U which are sufficiently big, this thing converge to 0 as t goes to infinity. So remember the UKT, they were neighborhoods of LK. So the measure of that set LK is always at most the measure of UKT, but that goes to 0. So the measure here of LK has to be 0. And since the measure of LK is 0, the measure of all the translated also 0, and you get what you want, that the Patterson-Sullivan measure only charges the radial limit set, or the K radial limit set, actually, for some K large enough. And the exact same proof will work with twisted measure. So you just copy paste the argument, adding a twist everywhere, and that will work the same way. So that's, yeah, I think I gave you all the arguments which are involved in this so-called hard direction. Is there any question?
Yeah, so one thing, so you've proved that this statistical, I mean, okay, so let me just call it statistical quasi-convexity.
Sure, no problem.
So
I'm not a big fan of either terminology, so you can call it whatever you like.
Yeah. So that implies that the Patterson-Sullivan measure charges only the radial limit set.
Yeah.
Is there a converse, or is it equivalent also? I mean, or is there a still weaker condition which guarantees this? Is there something that has been done along these lines?
So this is a question Iago asked me, I think. So I don't know exactly the answer. I need to check with the experts. I would be surprised that it is equivalent.
Okay. Yeah.
So yeah, I'm so maybe something. Yeah, probably. I guess probably there. I need to check. Probably there are examples where the Bowen-Margulis measure is finite, and because Bowen-Margulis measure is finite,
I see. Yeah. Okay.
The geodetic flow is ergodic, and therefore, using the Optogy-Sullivan theorem, the
radial limit set is full.
But you may have finite Bowen-Margulis measure without having a strongly positive recurring.
Okay. Thank you.
So I think this is not the same. And the fact is that the one difficulty somehow is when you have finite Bowen-Margulis measure, or generally speaking, when the geodesic flow is ergodic, you know automatically that the radial limit set has full measure for the Patterson-Sullivan measure. But that does not imply that the twisted Patterson-Sullivan measure only charges the radial limit set. And really, we need the strong positive recurrence to prove that the twisted measure only charges the radial limit set.
Yes.
Because the standard ergodic argument do not work in that context. Well, I guess if there is no other question, I'll wish you a good day.
So let's thank Remi for this beautiful course. And yeah, a lot of things to digest now. And thank you very much. Yeah, thank you very much. Yeah, thank you very much, Remi.
You're very welcome.